we're going to look at what happens when you have masses that are connected. The first example I want to look at is an Atwood's machine. Actually, before I say that, the key thing about when you have multiple objects, multiple masses, is that you can consider the entire system and consider Newton's second law with regard to the entire system, all the masses put together, or you can consider Newton's law for each object individually. And that's going to come into play when we start doing things with connected masses. So an Atwood's machine is a situation where we have a pulley, and we have a mass 1, and we have mass 2. Okay. And they're just hanging from this pulley, and we want to find the acceleration of our system, probably. Let's say mass 1 is 2.5 kilograms, and mass 2 is 3.6 kilograms. Okay, now released from rest up here. This is the ground. Let's think about the forces acting here. We have a gravitational force. On object 1, we have a gravitational force. On object 2, on object 1, we have a tension. On object 2, we have a tension. Now, even though these gravitational forces are acting in the same direction, they're kind of opposing each other because of the way these things are connected by this rope. And this will tend to cause the object to go down, which would pull this up, but then that gravitational force is opposing that. Okay. Now, if we consider the two objects as a whole, these tensions are pulling object 2 up, they're pulling object 1 up, and that is, those are two forces that are acting in opposition to each other, and the tension in the rope is the same throughout. So these tensions don't have any effect on the overall system. So on the overall system, the net force is that we have, if we'll consider this way, going up here and down over here to be positive. And so in that case, we have a net force of mass times acceleration, and this would be mass total times acceleration, and that would be equal to m2g minus m1g. Our total mass is just m1 plus m2. And so we wind up getting an acceleration, m2 minus m1g over 1 plus m2. This is how an Atwood machine basically functions. But we need to consider all the forces acting on them and consider the system as a whole. So m2 minus m1 now is 3.6 minus 2.5 times 9.8 over 3.6 plus 2.5. So that's what, 1.1 times 9.8 over 6.1. And we can punch that into our calculator and get that the acceleration of our system is 1.767 meters per second squared. Now say I wanted to find the tension in the rope. We know what the system is accelerating at, and so now we consider one object individually. Let's say block 2. On block 2, we know we have forces m2g and tension. And we know also that the acceleration of object 2 is the same as the acceleration of the whole system, 1.767, at the same value that I stored. So, for object 2, we can say mass times acceleration of object 2 is equal to tension minus mass of 2 times g. So the tension is just equal to the mass of object 2 times the acceleration of object 2 plus g, which is 3.6 times 1.767. We'll use the stored value from the calculator, plus 9.8. So that plus 9.8 times 3.6, we get the tension in the rope is about equal to 41.64, etc. newtons. So like I said, when you're dealing with connected masses, oftentimes you'll treat the system as a whole to figure something out, and then you'll treat the system, pick out pieces of the system individually to figure out more details. I want to do another example, and this pertains to our lab. So you've got a table, you've got a pulley on the edge of this table, you've got a block on the table, you've got a string connected to the block, and then there's a mass hanging down from the string. Right? What forces do we have acting? We'll call this, well, we'll just say there's gravity over here, there's gravity over here, normal force over here. There is no normal force over here because this is just hanging in the air. Sorry, this line is erroneous. Ground's down here. And then there's a tension in the rope that's pulling this block that way. There's a tension in the rope pulling this block that way. Okay. We'll call this block 1, block 2. There's also friction on block 1, and we'll say that it's sliding, so it's kinetic friction. Okay. Now let's say mass of block 2 is 4.5 grams. Mass of object 1 is, I don't know, 7.9 grams. And then we'll say that the system is accelerating at 0.51 meters per second squared. And I want to know, that's too big, 0.11 meters per second squared. It's probably still too big. Let's say mu k is 0.35, and I want to know the acceleration of the system, and I want to know the tension in the rope. Okay, so what do we have going on here? Well, if we consider the system as a whole, down and right are kind of in the same direction here. So the sum of our forces is equal to mass total, m1 plus m2 times acceleration, and that's equal to, well, going downward here, we have gravitational force on mass 2. Okay. Then the tension is internal to the system, so it doesn't have any effect on the overall system. And then all we have is this Fk. And we know Fk is mu k times normal force. And actually, if we look over here in the y direction, all we have are normal force and gravitational force. So the normal force here is equal to this gravitational force. So this becomes mu k times m1 g. And so this is the equation we can use to determine what our acceleration is. Our acceleration is m2g minus mu k m1g over m1 plus m2. And then from there we can start plugging in numbers. Mass of 2 is 4.5 grams. So that's 4.5 times 9.8 minus 0.37 times, I ran out of space, times 7.9 times 9.8 over 4.5 plus 7.9. Now you might say, at this point, you might stop me and say, hey, wait a minute, those masses are in grams and your g is in meters per second, or, well, yeah, these masses are in grams, don't we need kilograms? And that may be true in some cases, but since we have masses in the numerator and masses in the denominator, the units of grams are going to cancel out. And so it doesn't matter if we convert those to kilograms or not. So if I punch that in, 4.5 times 9.8 minus 0.37 times 7.9 times 9.8 divided by 4.5 plus 7.9, come out with an acceleration of 1.246 meters per second squared. So that's the first part of the problem solved. And this is the acceleration of the whole system. It's also the acceleration of each of the blocks. This is the acceleration of each of the blocks. If we look at block 2, we've got a tension, we've got a gravity, and just applying Newton's law, Newton's second law, we can say this mass times acceleration is equal to tension. Well, it's accelerating downward. So if we call this positive, then we have to make mg positive and tension negative. And therefore, the tension in the rope is mg minus ma. That's mass 2 in both cases. Mass 2. Now I do want to use I do want to convert to kilograms because nothing's going to cancel that out. 9.8 minus 1.246, etc. We'll use the stored value for that. So 9.8 minus answer times 0.045 gives us that the tension in this rope or string or whatever is 0.3849 and so forth newtons. Right? So that, again, like I said, when we're dealing with connected masses, the key thing to think about is that you want to apply Newton's second law to the whole system and then apply it individually to an object within the system. Now this is going to look a lot like our lab setup, part of our lab setup. We'll have a little truck here, and then we'll have masses hanging down in a box right here, and we will use this sort of strategy to figure out what we're doing in our lab.